Hello, my name is Christina and this is presentation 3. This is a PowerPoint explaining how heme is bound and released. I do have some note cards that I will be reading off of as well as the PowerPoint. Alright, so let's begin. Let us understand heme as defined on this slide. This definition I got from our textbook. Heme, a prosthetic helper group containing an iron atom. I place this image here depicting the heme group and the iron atom attached. I am going to be moving my little video around so that you guys can have a better look at the presentation. All right, so oxygen binding to heme and hemoglobin. Hemoglobin, the heme group, is non-planar when oxygen is not bound to it. So as you can see in this image, the iron is attached to the proximal histidine amino acid that is attached to the polypeptide chain. Since the oxygen is not attached, the iron is found below the plane. This is not the best image depicting the iron below the plane, but try and visualize and understand that the iron is below the plane due to its electron density. Now, another term to describe this form is deoxyhemoglobin, a form without the bound oxygen. So moving forward, this form with the binding of oxygen, as you can see here in this image, you see that the oxygen is binded to the iron in the heme. So this form with the binding of oxygen is known as oxyhemoglobin. Oxygen binds to the iron in the heme group and acquires a planar configuration. The non-planar shape of the heme changes to a planar shape to accommodate the oxygen now attached to the iron in the heme. The iron now lies in the plane of the porphyrin ring. When oxygen binds to the iron in the heme, it pulls away some of that electron density, allowing the structure to conform to a planar configuration. So as I stated, these pictures don't do it justice, but as a non-planar configuration and the oxygen not bound to the iron is shown below the plane. When the oxygen binds to iron, it pulls away some of the electron density from the iron, allowing the structure to conform to a planar configuration. So it kind of like lifts it up. All right, so I did want to put this image here so that you do see that the iron is attached to the proximal histidine and not the distal histidine as depicted in this image. Okay, so the quaternary structure of hemoglobin is constrained, existing in a tense state or T state. This state is changed on the binding of oxygen. So this 3D structure includes a pair of identical alpha-beta dimers and alpha-beta dimers that associate and form tetramers. So I put this image here so that you guys can see that there's alpha 1, beta 1, alpha 2, and beta 2. When the oxygen is not bound to the heme, it is considered to be in the tense state. Right, so oxyhemoglobin contains a much more relaxed conformation and is said to exist in a relaxed state or R state. Now I did want to add that as diatomic oxygen binds to the iron, it does pull the iron inward, which then pulls the proximal histidine, which pulls on the helix of the polypeptide chain. So as we see here, let's go back, this little line here kind of depicts the polypeptide chain that the proximal histidine would be attached to. And as the oxygen binds to, let's look over here, as the oxygen binds to the iron, it's pulling this iron up, which then pulls the proximal histidine, which is attached to the polypeptide. Right. So this changes the surface-to-surface interaction with the adjacent polypeptide chains. All right, bringing it closer. This change leads to cooperative behavior between the hemoglobin molecules, which leads to the other hemes having oxygen attaches to them as well. Now let's go ahead and discuss the release of heme. The release of heme, the way that heme releases oxygen correlates with the pressure in the lungs and in the capillaries. I really liked this graph because it does depict the pressure in the lungs as well as the pressure in the capillaries, and it gives you a great example of how the oxygen is released. So from our book, it does state that the pressure in the lungs is about 100 torr. So as you can see in the graph, at 100 torr, there is very minimal oxygen being released from the hemoglobin. In the lungs, the hemoglobin seemed to be fully saturated. As the pressure decreases, the oxygen is slowly released. Keep in mind that the capillaries are around 20 torr. So if we look at this graph and you see 20 torr, if you look up to this hemoglobin line, you see that it is very, very low, meaning that a lot of the oxygen has been released from the heme. So as hemoglobin moves throughout the body, thus transporting oxygen throughout. So for part 2, what would happen to the oxygen bond to hemoglobin if the pH of the tissue was the same as that of the lungs? So let's go ahead and consider the Bohr effect. And with the Bohr effect, there are signal molecules, hydrogen ions and carbon dioxide. These signal molecules enhance the release of oxygen. As we learned from chemistry, the higher the amount of hydrogen ions, the more acidic the solution. In the lungs, the pH is at 7.4, and in the muscle, the pH is 7.2. There are a higher number of hydrogen signal molecules in the capillaries and the muscles than the lungs. The pH change allows for the release of oxygen. So if there is no change in the pH, the Bohr effect will be no more, and the metabolic activities of tissue will be no more. So thank you very much for listening, and have a good night.